Welcome back to the GD&T Master Course for Lesson 5. So I want you to picture this. You've got a machined mounting bracket, right? And it's just floating freely in three-dimensional space. Maybe it's hovering right above your desk. It can drift up and down, it can slide side to side, and it can spin end over end. Today's explainer is all about how we mathematically and physically capture that floating part. We're going to build a cage around it and lock it down using datum reference frames. Because honestly, until we restrict that movement, that part absolutely cannot be manufactured or inspected reliably. Here's our roadmap for today. We'll start with the 6 degrees of freedom, then move into building datum reference frames, reading feature control frames, looking at real-world manufacturing and inspection applications, and finally, we'll wrap things up with some of the most common GD&T mistakes. All right, let's just dive right in with a pretty massive question. Since we design all our parts in a fully three-dimensional CAD environment, you might be wondering, why can't we just pick one single bottom surface, call it our datum, and call it a day? Why do we actually need this whole complex system in the first place? Well, to answer that, we're jumping into Section 1, the 6 degrees of freedom. We really have to break down exactly how an unconstrained part behaves out there in space. Okay, take a look at this table based on the ASME Y14.5 standards. You'll see that every unconstrained part in the universe has exactly 6 degrees of freedom. First off, you've got 3 translations, meaning the part can slide back and forth along the x-axis, the y-axis, and the z-axis. But on top of that, you have 3 rotations, right? The part can pitch, yaw, and roll around those exact same 3 axes. Just imagine the front of the part tipping up and down for pitch, turning side to side for yaw, and tilting over for roll. So if you only specify a single flat surface as your data, yeah, you might stop it from translating up and down, and you might stop a couple of those rotations from tipping over. But that part, it can still freely slide around on the table like a hockey puck, and it can still spin like a top. To apply geometric tolerances that actually mean something, all 6 of these degrees of freedom absolutely must be definitively constrained. Moving right along to Section 2, building datum reference frames. The crucial point here is that to stop that free movement entirely, we have to build a highly stable framework around the part. And we do this by creating what's called a datum reference frame, or DRF. Now, I'll be honest, this is a concept that trips a lot of people up because it bridges 2 fundamentally different worlds. On one side, we have the theoretical perfect geometry, the flawless, mathematically pristine planes and cylinders that only exist inside your CAD software. But out on the shop floor, physical perfection just doesn't exist. So we use what the standard calls a datum feature simulator. These are the real, physical manifestations of those perfect theoretical planes. Think of a highly calibrated granite surface plate, a precision chuck, or a custom collet. These physical simulators are what tangibly lock the part down so it can be reliably machined or checked with a coordinate measuring machine. Let's see how this actually builds using the famous 3-2-1 positioning principle. This is literally the core of any GD&T setup. You start with your primary datum, which is usually your largest, most stable mating surface. It requires a minimum of 3 points of contact to establish a plane. Doing this immediately removes 3 degrees of freedom, specifically 1 translation and 2 rotations. Next up, you push the part against your secondary datum, which requires a minimum of 2 points of contact. This establishes your orientation, stopping the remaining rotation and removing 1 more translation, so that removes 2 more degrees of freedom total. And finally, you slide the part against the tertiary datum, which only needs 1 single point of contact. This acts as the final locator, removing the last remaining degree of translation. 3, 2, 1, boom. Your part is now completely and reliably locked in space. Which brings us to Section 3, reading feature control frames. Now that we understand the mechanics of how to mathematically and physically lock a part down, how do we actually communicate this vital information to the machinist or the inspector reading the print? Check out the datum precedence order right inside the feature control frame here. See those boxes on the right showing an A and then a B? That order, reading left to right, is everything. Precedence absolutely matters. The primary datum A dictates the stringent foundational plane. The part must sit perfectly flush against A first. It's only after A is fully engaged that the secondary datum, B, comes into play to square things off. If an inspector were to reverse this and align to B first, they'd tilt the part differently, and perfectly good parts might literally fail inspection. The feature control frame explicitly writes the rules of engagement. You've got to follow the order. Let's move to Section 4, manufacturing and inspection applications. We're going to take this theory off this sterile drawing board and throw it out onto the noisy, messy manufacturing floor to see how it really behaves. Right here, you can see exactly how a real machined bracket gets inspected using a physical go gauge. Notice how the gauge is basically designed as a negative shape of the part. The flat bottom of the gauge acts as that primary datum A simulator. The part rests right there, then it gets pushed against the long side wall, which acts as secondary datum B, and finally, it slides right against the short wall, tertiary datum C. It perfectly mimics that 3-2-1 principle we were just talking about. When you're mass-producing thousands of these brackets, this physical datum reference frame guarantees that the inspector is loading the part the exact same way every single time. And the applications here span across the entire manufacturing sector. Whether you're doing model-based GD&T, using digital CMM alignments for complex aerospace structures, or you're evaluating the warp in injection-molded plastic housings, or even checking the form on stamped sheet metal parts, a functionally proper datum reference frame is the absolute bedrock of your process control. And I really, really cannot stress this enough. If your datums are wrong, your process control is practically non-existent. Finally, Section 5, Common GD&T Mistakes. Because, let's be real, the gap between engineering theory and shop floor reality is where things usually go wrong. And trust me, they go wrong often. Industry experts from Sigmetrics frequently point out that the #1 mistake engineers make is just overcomplicating their designs. They'll choose non-functional datums just because they're super easy to dimension in CAD, entirely ignoring how the part actually mates in its final assembly out in the real world. They'll also select unstable features, like tiny warped edges or rough cast surfaces as a primary datum. That just makes the part wobble all over the place during inspection. Doing this is a surefire way to take a perfectly good functional part and make it look like expensive scrap on an inspection report. To show you just how frustrating bad datum selection can be for the people actually building and inspecting your designs, take a look at this real complaint from an engineer on Reddit. They wrote, and I quote, "I once had to make a CMM program for a part with one foci of an ellipse as a datum point. There is a pit on the lowest level of engineer hell waiting for whoever made that decision." I absolutely love this quote because it's a stark, painfully funny warning. Never ever pick imaginary points in empty space just because they look neat on a computer screen. Your datums must be tangible, accessible, and measurable physical features. So to summarize this explainer, just remember that datum reference frames are the absolute anchor of GD&T. They use the 3-2-1 positioning principle to strip away all 6 degrees of freedom from a floating part, bridging theoretical design directly to the physical reality of manufacturing. You always want to choose datums that are functional, stable, and reflect how the part actually assembles in the real world. Now, I want to leave you with this final provocative thought. If your datums aren't functionally mimicking how your part fits into its final assembly, what are you actually measuring? And why are you measuring it? Keep that question in mind as you look at your next drawing. Next lesson, feature control frames and how to read GD&T callouts.